You want me to review the free response first? Okay, so let's do the free response first. All right, so we're gonna have three big problems. Each of them will have 2 or 3 parts for a total of 8. You're gonna have a conservation of energy problem. We've worked these over and over. I'm just gonna make up a problem, and then we'll work through it. Let's say that I have a cart here. Say that the mass is, I don't know, 2 kilograms, and that the height is 4 meters. And let's say that its initial speed is equal to 3 meters per second. And then I would have these labeled A, B, C, and then up here at D is where the cart would come to rest. I would just say that in the text of the problem. And I could ask several things. Let's say that B, by the way, is at 2 meters high. So I might ask you, for example, what kind of energy does it have at point B, right? What type of energy? And then you would say potential energy and kinetic energy, right? It has both of those. And the reason it has kinetic energy is, well, you know it has a kinetic energy up here at the top, so it's also going to have kinetic energy up here. It'll still be going at those lower heights. At point C, for example, it would just have kinetic energy because H equals 0, potential energy is 0. And at point D, it would only have potential energy, assuming that the speed of the object up there is 0. I think we're all good on that, right? And then, so I might ask, what is the speed of the object at point B? In which case you would say the kinetic energy at the beginning plus the potential energy at the beginning is equal to the kinetic energy at part B plus the potential energy at B. That would be 1/2 m. I'm going to go ahead and put in the speed here, 3 squared, plus m times 10 times 4. The 10 is g, right? And it's positive 10. That's equal to 1/2 m times v squared, where v is what I want to know, plus m times 10, which is g, times 2, which is the height here. And then you would cancel out your m's. I mean, you have the mass, but it's easier if you just cancel them out. You just have fewer numbers to work with. And then you solve for v. So here, 1/2 of 9 is 4.5 plus 40 minus 20 equals 1/2 v squared. That's 24.5. That's 48, 49. V squared is 49. So V is equal to square root of 49 and 7, right? Yeah. So that's the answer. Okay? I might also ask you what's the total amount of energy that something has, in which case you would just, calculate this. That would be the total amount of energy. You're also going to have some multiple choice questions. So make sure that you get this question because it's 5 or 6 questions that you'll have that will be part of your test. Okay? Big deal. But they should be easy for you to do if you've done it a few times. Right? Not that hard, right? Not that hard? Not that hard, Spin? The energy stays the same. The sum, the total amount of energy, which is the kinetic plus the potential, remains the same the entire time. Okay? And then also be aware there's other little questions I might ask. What types of energy does it have here, or what is the total amount of energy? The second problem, I've already told y'all in class, but it'll look like this. You'll have a inclined plane, and let's say that this is a certain distance. I'm just going to go ahead and give you the distance, though, I might give you the sides, and you have to use the Pythagorean theorem to figure out that distance. Let's just say that this is 7 meters. And let's say I have a block that's moving down the inclined plane, and let's say that it has a certain speed at the top. Say the speed is, 5 meters per second. And I tell you that there's a frictional force that is equal to 2 newtons. And I want to know what is the speed at the bottom. I'm not going to require you to figure out the normal force on an inclined plane. So all that stuff with vectors we did in chapter 4, not going to come up. I know that there were 1 or 2 problems in the past exams where the students had to, do the sum of the vectors in 2D and figure out the normal force. I'm not going to make you do that on this test. Is that clear? Okay. So even though there will be an angle here, or, I might not give you the angle, but you could, of course, figure it out because you'll know the hypotenuse and or one of the sides. Even though there will be an angle right there that I won't give it, what's the answer? You won't need it. You won't need that angle, okay? So, I have this block at the top. It's a certain height. I can figure out this height. Let's say that it's 3 meters, for example. And you need to tell me what is the speed at the bottom. This is a lot like the roller coaster problem. The only difference is that you have to account for the friction. So the way this would work is, at the beginning, the object has kinetic energy plus potential energy. I think the example in the exam, it's stationary at the top, so it only has potential energy, if you've seen some problems like this on the old exams. So if V was equal to 0, you wouldn't have that kinetic energy term. So this is the original energy. And then I'm going to subtract the work done by friction, and that will equal to the final energy, which is only kinetic energy. Still saying initial equals final, except now I'm subtracting this term because that frictional force is a non-conservative force. So it takes away energy from the system. And so this would work out in this way. You're going to need the mass. So let's say the mass is 2 kilograms. That's going to be 1/2 of 2 times 5 squared. The 2 is the mass, the 5 is the speed, plus 2, that's the mass, times g, that's 10, times h, which is 3. Let me write in these variables. So I have 1/2 mv squared plus mgh minus the work done by friction, which is 2 newtons, times the distance, which is 7 meters, minus, this is minus the force, times the distance, and then that's going to equal to, I've run out of space, I'm going to do it down here, that will equal to the final kinetic energy, which is 1/2 m, which is 2 times v squared. I'll move it up, Carly. I think you can see that. Okay? So the red, I'm sorry, these are just the variable names I was writing in, but the red is the equation. So that's going to be 25 plus, what's that, 60 minus 14 equals 1/2 of 2v squared, so it's just going to be v squared. 85, 81. 71 equals v squared, and then you square root that, it's going to be v. No, you can't cancel out the 1/2s. Be careful on your canceling. Don't get crazy with canceling, because notice I only got a half here and here, but when I have these additive terms, when I'm adding up terms, that 1/2 has to be in every single term. That's, by the way, in this problem, why I can't cancel out the m's. Notice usually, like in that previous problem, I can just cancel out all the masses, but when you have the frictional force in this case, I don't cancel out the masses. But you're saying, I worked a problem where I did cancel out the mass. But in that case, y'all remember that problem? Some of y'all have seen it. I know you've seen it. Where you had to find the mu. The frictional force is actually dependent upon the mass, because the frictional force, you recall, is mu times the normal force. And when you're on a flat surface, the normal force is equal to the weight. When on a flat surface, this is equal to mu mg. Not now, because we're on an incline and it's more complicated than that. But since I gave you the frictional force, you don't get to cancel out the masses. Okay? Practice those. That's your second free response problem. And it's going to be, I think it's just 2 questions. I might ask you, what is the total energy at the top? What is the work done by friction? And what is the velocity or the speed at the bottom of the ramp?
So is this set of questions just in the free response, or is it in the multiple choice?
It's in both. So I don't think that there are work energy problems. I don't remember if there's an inclined plane. there might be a conceptual inclined plane. You've seen several of those at various times throughout the class. But there are definitely work energy problems in the multiple choice part of the test. One or two at least. Yeah, Claire?
How would you find the work done by friction?
Okay, so define the work done by friction. That was this term right here. Let me write it out. The work done by friction, the work done by any force, is the force times the displacement times the cosine of the angle between the force and the displacement. But in this case, I've made it easier by saying that the force and the displacement are in the same direction. Or actually, they're anti-parallel. They're in the opposite direction. So this thing just goes away. So it's just the force times the distance. So that's going to be 2 newtons times, what do we say, 7 meters, I think, or 14 newton meters, or 14 joules. Good question. They're all good questions. Y'all ask great questions that you'll probably see again on Monday. Yeah, if you want to know the total energy at the top, that would be this term right here. You're right. And then that work is taking energy away. Okay? Oh, no. Sorry, I'm sloppy on this, aren't I? So this is kinetic energy at the top and potential energy at the top. This is kinetic energy at the bottom. So those are 2 different terms. Okay? This is the top, this is the bottom. Good question. All right, and third thing is a collision problem. That is, we'll make it easy for you because I'm going to give you a picture of 2 objects. They'll be moving, for example, towards one another. They could be moving in the same direction, by the way. Like one of them could overtake the other one and collide to it. Let's just do one like that because we've done these before. Let's do one like this. They're the same. Like it doesn't really matter. Let's say that this one has a speed equal to 5 meters per second, and this has a speed equal to 1 meter per second, right? Like back in, when was that? Over the summer, my wife got rear-ended on the Shaver overpass by a Nichols student. He was really nice about it. This would be like a rear-end collision, right? Somebody running into the back of you because you're going faster than the person in front of you. Listen, they had just gotten back from Dishman's Flooring, and they bought 3 gallons of paint. And when that guy ran into the back of them, all those paint like exploded inside our van. So if you ever drive on a Shaver overpass, there's a little puddle of paint like on the on the shoulder. I think it's gone now, but there's a little puddle. That's my wife and my daughter. Our van was completely totaled. We missed that van. All right, so we'll call this V1. We'll call this V2. These are the initial velocities. So we'll say that this mass is 1 kilogram, and we'll call this mass 2 kilograms. And then let's say that after they collide, so that's the initial state. By the way, one question I might ask you is just what is the total momentum? The initial momentum then would be 1 kilogram times 5 meters per second plus 2 kilograms times 1 meter per second. And so that would be 7 kilogram meters per second. That's the initial momentum, but it's also the momentum at any point during time, that this system will always have the same amount of momentum. Then after they collide, I would tell you, okay, well now this guy is now going at a final speed, V1F I'll call it, of 2 meters per second. Is this going to work out? No, let's not do it that way. Let's make it more interesting. Let's say that this guy then bounces back at a final speed of 2 meters per second, and I want to know what is the velocity of this guy. And I wouldn't tell you the direction, but what is the final velocity of this guy, V2F? Excuse me, I'm sorry. This is V1F. I feel scattered today. I made a lot of mistakes in class this morning too, right? I used to wait tables, And when we would drop a dish, what'd they do? Take it out of your check? They should do that to us too. Like whenever a professor makes a mistake, they should take it, deduct that out of your pay. Like figure out some scale. Y'all don't like that, like yeah, right. Or maybe if you catch the mistake, that you get a little, like having a swear jar or something. Okay, so this is 1 kilogram. So I would say that this 7 kilogram meters per second, that's just what I found up here, is equal to 1 kilogram, watch this, watch it, negative 2 meters per second. Okay, be careful, make sure that if it's going to the left, that you get a negative written in there, plus 2 kilograms times V2F. And then you just solve for V2F. So I get 7 plus 2 divided by 2 is equal to V2F. So that means that this thing is going to be going in this direction at 4.5 meters per second. 7 plus 2 is 9. 9 divided by 2 is 4.5. Okay? The thing that you're going to miss, the thing that a lot of students will miss, unfortunately you'll get half credit if you do this because you'll have it all laid out nicely and I'll see your equations written properly, but the thing that you're going to miss is you're going to miss this. You're going to miss the signs. I mean, you're not because y'all are awesome, but a lot of students are going to miss the signs. Okay? Be very, very careful with the signs. I sat with like 3 students this morning. Every single one of those students, I think every single one missed a sign at one point.
So, what would you call this collision?
Oh, so what type of collision? So that's another question I'll likely ask you. If they make contact, that's always an inelastic collision. But you know, that's what we're going to have. We're going to have an inelastic collision. You could have an elastic collision where you have 2 particles that interact but don't collide. But we're not going to see that. Like if you had 2 charges moving together and then they bounced off one another because of the field forces, but we're not going to get into that. We'll see that next semester.
So always be inelastic or perfectly inelastic?
Yeah, see, if it, just like Laura, so if it's inelastic, that's if they have contact. And then if they stick together, then that would be a perfectly inelastic. Laura? Oh, no, let me show you what I did. I was doing that quickly. So this is negative 2, and then I added 2 to both sides. Let's see, I have 7 equals negative 2 plus 2 V2F. I added 2 to both sides. 7 plus 2 equals 2 V2F. Sorry, sometimes I get ahead of myself. You should get $2 right now. Elena, I'm going to propose that to the president. It was your idea. Does he know you? No, okay.
Probably not.
Probably not. Okay. Those are the free response. What do you want to look at on the test? Do you have particular questions on the test? What's that? Oh, momentum. Okay. Like conceptual or let's just see. So the type of problem that we haven't worked in momentum. Let me find one that's okay.
You were saying it, and then I wasn't able to write it down before.
Did I say this in class today or?
Oh, here I have it.
Yeah. I don't remember what I said there. Is that when I made the comment about faculty having to pay for their mistakes?
No.
Cause
It's okay, I got it.
is somebody recording this? Oh wait, I'm recording it. Okay. Momentum. So we've done collision problems, and you'll see some in the test. It's a multiple choice, like number 21, for example, and number 22. By the way, both of these are straight from the concept test. So be sure to review those. Those are on Moodle. Like I said, pull them up on your phone or print them out 6 slides to a page and just quiz yourself on them. Oh, I'm sorry. This is fall 2020, which unfortunately is not in your book, I understand. Let's look at 21. So I have this sack of coal that's dropped onto a 2,000 kilogram railroad flat car that's moving at 3 meters per second. And then the sack just falls flat onto the flat car. And I want to know what happens to the speed of the flat car. Now, we've seen a similar problem. Remember the problem with the rain falling into the cart? And when the rain falls into it, the mass goes up. And that means since the momentum remains the same, that the speed goes down. That P is equal to mv. So if the mass goes up, that means for P to remain constant, V has to go down. So I know that the speed of this thing has to be less than 3 meters per second, so I can get rid of E right away. I still have 4 answers, so that doesn't help me a whole lot. But the initial momentum, I know, has to equal to the final momentum. And the initial momentum is 2,000, that's the mass of the flat car, times 3 meters per second. That's its speed. And the final momentum, this is a perfectly inelastic, it's a perfectly inelastic collision. That means that the two objects come together and stick together and move off at the same speed. That's 2,500 times VF. So that's 6,000 divided by 2,500. 60 over 25. It's like 2 point something. 2.4 is the answer. Okay? That's a momentum problem, just like on the free response, but it looks like I see y'all's hands. It looks different, right? So drawing a picture will help. Well, I mean, I already have you a picture here, but think about it in the same way, that this is a collision between two objects. Kennedy and then Claire.
Okay, so, the one under it.
We're gonna do that one in just a second. You want Claire?
Yeah, okay, so, it doesn't matter how it sticks.
Yeah, it doesn't matter.
Okay. And initials always equal to final?
The initial momentum will always equal to the final. Can I say something like just complicate you and confuse you? It does matter a little bit how, like, if the bag of coal, like if it exerts a forward force, then momentum is no longer conserved. But we won't ever have that. Okay? Kennedy?
Okay, so when I was setting this one up, I had trouble, like, what if you put the two girls in opposite places? Because when you did it on a video, you put, like, Gwen, who is the bigger girl, on the left side, and then Amy on the right side, and then the directions were, I think, like, if you switch places with the directions the opposite from each other, would it change anything when you're solving for it?
It doesn't matter about direction here, so she asked about the direct, like what if the two people that just have their positions switched. It doesn't matter in this problem because we're just looking for the speed. And the speed is a scalar quantity, it means it doesn't have a direction, so it doesn't really matter if it's negative, if it's positive. I'm really only looking for the magnitude. But this is sort of like the uranium fission problem that we looked at this morning. You remember that one at the very end? I have two people. I'm just going to show them as blocks. So this is Gwen, and this is Amy. Right? One bigger than the other. And Gwen is like 3 times. Amy's just a little bitty kid, and Gwen is like an adult. They initially have a momentum equal to 0 because neither one of them is moving. But then they move off in opposite directions because they push off on one another. Now, Gwen, who is 3 times as big, is going to move a third as fast. So Amy is going to have a much bigger speed. So here, Amy goes away at 10 meters per second. So this is 10 meters per second. Can you guess what the answer is? The answer is A, because Gwen is going to be moving 1/3 the speed of the smaller girl, or the little girl. Let me show you how that works out. So this is 150. It's a weight, but we'll treat it like a mass. This is 50, and so I would say 150. I can't see that clearly. 150 times her speed is equal to 50 times 10. And so V is 50 over 150 times 10. That's a third of 10, or 3.3, or just 3 meters per second.
So if you put Amy in Gwen's place and you had 10 meters per second going the left direction, it wouldn't change the sign, or it wouldn't like affect the magnitude?
Yeah, I mean, I was a little sloppy with my signs here because really all that I was doing, since I knew that I wasn't really concerned about direction, all that I was doing was saying this momentum is equal and opposite to this momentum, right? That they have to add up to equal to 0. And then I just sort of discarded the signs. Now, if I really want to be rigorous about it, I would say we'll call this P1, this P2. I would say 50 times 10 plus 150 times V is equal to 0. And then I would get V equals to negative 3.3 meters per second. You see what I mean there? But I don't have to worry about all that because I don't need the sign anyway.
You just want to know the number.
Yeah. Elena?
And the ones that you do need the sign for, especially like when you have the person and they're throwing the ball, how do you know which direction they're throwing the ball?
I'll say in the problem, okay? And if I don't, it's not important. Yeah, there aren't that many. Let's see. Somebody know where one is? You want to help? So a problem where the direction is important. No, I don't think the direction's not important on this one either. No, now you would do this the same way, where you're starting with a momentum of 0, and then you end with a object going at mass of 60 kilograms times its final speed, plus 3 kilograms at 10 meters per second. All right, this is the initial momentum. It's equal to the final momentum. So it's 0 equals 60 VF plus 30. So VF is equal to, well, it would be negative 0.5. But again, I'm just looking for the speed, not the velocity. It's rare for me to ask for the direction on these types of problems where I have just they're stationary at the beginning. Really, the ones where the direction is important are the collisions where you have a single object colliding with an immovable object, like the car running into the wall. That's where you got to be careful with your direction. But as I told you, if you have something that's rebounding off of a wall, like it's going in one direction and then the other direction, just take the sum of the two, and that'll you'll be able to get that's your change in velocity. You understand what I'm saying? You have that minus and negative. Let's find one. Number 21, the direction is important. We'll look at that one. Is that the one you intended? 21?
Oh no, I was just spitballing around.
Okay. Yeah, there's some good questions on here. Remember impulse? What is impulse, y'all? It's just change in momentum. Okay, just fancy word for change in momentum. Let's go back. I want to work these problems. Number 21 would really help you to draw a picture. So if you got a bunch of words, just start drawing a picture. You should have plenty of time for the exam. Like it's normal length, but take your time and just draw a picture. So my first mass is moving at 2 meters per second to the right. So I have my 11 kilograms moving at 2 meters per second to the right. And then M2, this is my second mass, M2. And it's initially at rest. After an elastic collision, that means that energy and momentum are conserved. But as far as we're concerned, we're really just concerned about the momentum being conserved. the first mass goes back this direction to the left with 1 meter per second. And I want to know what is the velocity of this object. Okay? Now, I gotta look at this and tell you that it's almost certain that it's gonna be to the right. Not almost certain, because look, I have a positive momentum here, because it's to the right, but this one's to the left, so it has a negative momentum. So this one has to have a positive momentum that's bigger than this momentum in order to give the overall system a positive momentum. So let's just work it out. So I have 11 times 2 equals 11 times negative 1 plus, what was that mass? 22 times v, and that's the v I want to know. So I get 22 plus 11 divided by 22 equals v. My 22 does not cancel out. It's 33 divided by 22. That's 3 halves, or positive 1.5. Is that right? 3 halves? Yeah. Yeah, Claire, what you have a question about this?
How do you know when the momentum is 0 and when it's positive?
So if the object is not moving, it has 0 momentum. So up here, I knew that this object had 0 momentum because it said mass m2 is initially at rest. All right, so remember, momentum is mass times velocity. It's not moving, 0 momentum. Same with the Amy and Glenn problem. Neither one of them was moving, so that each one had 0 momentum. That's why I said in that problem that 0 is equal to, like I lumped them all together and said they both have 0 momentum. 19? Yeah, so I tell you here what the initial momentum is for each. One of them has positive 30, the other one has minus 20. So the initial momentum is minus 10 kilogram meters per second. So you don't have to deal with all the masses and velocities. I just add those two together like vectors, 1D vectors. That's why one of them is negative. And then I'm going to set that equal to, negative 10, equal to the final momentum. So negative 10 is equal to the mass final times the velocity final. But this is a perfectly inelastic collision. So the final mass is 4 plus 1. They stick together, and those are the two masses, 4 and 1, times VF. So VF is going to be, oh, shoot, I should have been, I want to be a little more careful on this, don't I? VF is going to equal to 2, but it's going to equal positive 2. Let me show you why it didn't come out positive. I get in the habit of just setting one momentum equal to the other, but really the momentums are, wait, how does that work? Hold on. Oh, it's not negative. That was my mistake. Never mind. This was positive. Y'all see that? $2 again. Tell President Clune this should be positive, so this would be positive 2 meters per second. Be careful. Yeah. I'm not finding an impulse. An impulse is a change in momentum. I'm finding the momentum. I appreciate you using that word, but that's not. Impulse is a change in momentum.
And that's when you would like subtract the momentums to give you the P initial instead.
Do y'all know what the plural of momentum is?
Momenta.
Momenta. There you go. What was I saying?
When you're finding PI, why would you subtract them?
Oh, because I have two particles. Two particles, and I want to know what is the total momentum. So I add up the two momenta.
problem?
Impulse? Yeah. They're not hard once you do them. You just sort of have to know what impulse means. Like number 24. Who asked that? Julia? Claire? All right, so I want to know the impulse. Delta P is my impulse. That's I. And it's equal to m delta V divided by, excuse me, not divided by, just m delta V. I think this is on your equation sheet, by the way. Isn't impulse on your equation sheet? I don't know. We'll look. And so that's going to be the 2 kilogram mass, 2 kilograms, times VF minus V initial. VF is 3 minus V initial, which is negative 4, times 2. That's 2 times 7, or 14. But notice, if you got these signs wrong, you wouldn't have put 14, you would have put 2. But of course, that would have been wrong. So be careful with the signs. This chapter, more than others, the signs are really important. Okay? Lena?
I know how to do it, but the equation sheet says negative K, so what if we use a negative K versus a positive?
Yeah, so Hooke's law says that F equals negative Kx. Let me show you why it says that. So this is my equilibrium position. Now let's say that I compress my spring this distance. This is x. Notice if this is x equals 0, then this is a negative value. Okay? So, but the force that the spring exerts is in that direction. So F is always opposite x. They're vectors. They are both vectors. And since F is always opposite x, that's why you have this negative here. Your spring is always going to tend back towards the equilibrium position. So for example, if your spring is stretched out over here, here you have a positive x, but your force due to the spring is in that direction. So x is positive, but the force due to the spring is negative. So that's why that negative is there. But I don't usually use the negative. I'll calculate F, and usually when I write this, I'll just say Kx. But then I go back and I think about the spring. If it's particular to the problem, what is the direction of the force that the spring exerts? Those pictures are useful in that case to help you think about that. It's not usually important, but you're right, sometimes it is important. It doesn't change the value of the force, the magnitude, but if the direction is relevant in the problem, then it is important. I don't even know that there are any problems where that direction is relevant. Are there? Where was that? Oh yeah. So here, I know that my force due to the spring has to be in this direction. So I can get rid of these answers right away. And then if I want to know the force, it's equal to Kx, which is 1,000 times 0.5. 1,000 newtons per meter, that's K. And then 50 centimeters are 0.5 meters. So the answer is 500. So there were several things going on here in this problem. You had to realize the direction. You also had to realize that you had to convert this to meters, two decimal places over. Because if you miss either one of those points, you're going to get the answer wrong. That's why I gave the picture in this case, so the students would see that and say, oh, it has to be a positive force. You could see something similar to that. I say those students, y'all too, like this. Y'all should be able to do that. Now you can, for sure, right? Like you see, you'll get it right. All right? Kennedy? What is it?
So, if you drop a ball off of like a building and hit somebody on the head and it rebounds up,
Yeah.
would that hurt worse?
A lot worse, yes.
It just dropping on somebody's head and then just falling down.
Yeah. Yeah, it would hurt a lot worse. That's like the rat tail thing. That was the whole point. Like, if you flick it out and then bring it back, it hurts worse because you get a rebound velocity, and your impulse then, your change in momentum, is more. And since your impulse is bigger, delta p over delta t, if this goes up, that means the force goes up. And the force, the bigger the force, the more the pain.
When you're comparing, like the kinetic energy to the velocity and the momentum, when do you use the square root 2 and the 4?
Somebody's asking me this question this morning. I think 2 students actually. So I don't know where the question is. Do you know where? There are a couple like this. They're straight from the concept test, by the way. I know we didn't do that question in class, but y'all review the concept tests. They're on Moodle. Print them out. Do whatever you need to do. Put them on your phone. Just slide through the slides. So it was something like an object has a kinetic energy, and you increase it by a factor of 3. The kinetic energy of an object is increased by a factor of 3. 3 times. That's a times, that X symbol. What is the new momentum? How much is the momentum increased? So that's right. So kinetic energy is 1/2 mv squared. Momentum is m times v. If I triple my kinetic energy, my mass remains constant, but how much has my speed increased? Let's say I quadruple my kinetic energy. By how much has my speed increased? What did you say? You said it, Kennedy.
I don't know what I said.
What did you say?
So it would just be 4 squared, right? Like,
Not 4 squared, because if I put a 4 right here, that gives me a 16 over there. Twice. So the speed would be double in order to get 4 times the energy. But what if this is 3? By how much has my speed increased? What's that, Austin? Not 6, no. Good guess, but I'm going to just make this bigger so I can... Not 1/3. What times itself is equal to 3? Don't answer. What times itself is equal to 3? Come on, y'all. Y'all didn't learn your multiplication tables? No, not 1.5. Not 3. What times itself is 3? Square root of 3, right? Root 3 times root 3 is square root of 3. So if I triple my kinetic energy, that means that my speed is increased by a root 3. And then, so if my speed is increased by root 3, then my momentum is increased by root 3. 1.4. No, that's not 1.4. Whatever that is.
So, kind of like if you're going from kinetic energy to the velocity, then you use
Right, so if I have 1/2 mv squared and say I double my speed, then that means that I have 4 times the kinetic energy. The point is that this number has to equal this number, 2 squared. And it's squared. So that was true here, that this number, 3, is equal to square root of 3 squared. It's just a square root, right? And that's right. It's always going to be the square root, right? You just have to make sure that you get them in the right order. The number on the left has to equal the number on the right. The change, the factor that you introduce on the left or right has to be the same on the other side of the equation. That's not a hard physics question, but it's a hard math question to just sort of think about those sorts of relationships. It's an important thing. Like that's a good MCAT question, for example. They love those sorts of things. Huh? Yeah. I have to go soon, though. I'm going over to the shop. So that's why I'm in my digs today. How you like my digs? Shorts? You've never seen me in shorts, have you? Alright, what are we doing? A work energy problem? We've done all these. Let's go down a ways. Boy, we've done a lot of them. Okay, here's one, number 2. This is like the one we did in the beginning when I was laying out the free response, and this is similar to what you have in your free response. 10 kilogram kid comes down a slide. I'll throw on my block. He has a mass of 10 kilograms. The slide is 2 meters high, 2 meters, and then it's also 4 meters long. And there's a frictional force of 5 newtons that acts on the kid all along the entire length of the slide. At the top, he has potential energy. Remember the first time I showed you, he had a speed, so he also had a kinetic energy. So he has a potential energy at the top, and then I subtract the work that's done by friction, and that will equal to the kinetic energy at the bottom. Okay? So the potential energy at the top is mgh minus the force due to friction, and the distance, that's going to be our 4 meters, is equal to 1/2 mv squared. Notice my masses don't cancel here. I can't cancel those out. So that's 10 kilograms times 10 meters per second squared times 2 meters minus 5 times 4. The 4 is this distance, equals 1/2 of 10 times v squared. It's 200 minus 20, that's 180 divided by 5 equals v squared. It's 30 something. I don't know what the 30, is it 36? 5 times 36 is 180? Oh yeah, so it's 6 meters per second. Okay? That's a good work energy problem. That'll be a lot like your free response. Faith, did you ask that question? Yeah. All right. Okay to stop here, y'all? Okay.